So, good evening. So, welcome to the week 10 of Fundamentals of Combustion close. So, we'll wait for 1 or 2 minutes for anyone to join. Then we'll start the session. So we'll start the session. So welcome to the week 10 of the live session on Fundamentals of Combustion course. So this is a 2-hour session. So first 1 hour we will try to see in brief what are the things that were taught to you in week 10, and in the second half we will try to solve some problems which will eventually help you in solving the assignments. So in the brief outline of the course, we will be mostly this week 10 we will be dealing with different types of combustion processes is a broad topic that we are dealing with, and in that we will mostly deal with turbulent premixed flames, and some part that was left in diffusion flames you will see, and then the turbulent premixed flames. When you are having turbulent flow, how the premixed flames and all behave, that's what was main focus in week 10. So I'll move on to the tab. Okay, so in the last class we stopped at considering the things on studying the effects of partial premixing was where we stopped. So in order to control the combustion characteristics in such, so you remember the conditions wherein I will confirm. So So we were talking about premixed flames and diffusion flames, and we were talking about the effects of having a partial premixing. So we saw there were different flames. So you saw shown in week 10 the different flame heights and flame structures that are getting affected when you are having a premixed flame and a partial premixed flame and all this. So when I say partial premixing, your primary air is added with the fuel to control the combustion characteristics in in sooty flames, which when you are having, in order to reduce the sooty flames, so you will have an opening which we might have seen in the videos, where when you are having 0% of air, only fuel is being gone, you will see a sooty flame where you are having your tip being opened up, producing a lot of soot. But once you introduce more and more air, you will see that your flame gets closed and you don't have that smoothy thing coming up. So if you consider a LPG plus air mixture, here the 40% of stoichiometric value is the thumb rule value, where above which you will have a premixed flame. So you might remember that you had a figure like you had a flame like this, but there was opening and you had soot coming out, and as you increased your percentage from 0 to 20% of air, you saw that there is a flame but it is being closed, and you saw there is a bluish region here, and as you increase to 40%, your bluish region further increased up, and once you reached a particular above 40%, your flame length remained almost close to same, and your bluish region it started changing off. So you saw this variation and the color photos that were shown to you in the week 10 video. So major thing that you need to learn from here is like the flame height decreases significantly when you are increasing, when your fuel flow or the air percentage of air flow rate sending is below 40%. You will see that there is a change in the flame height, and soot formation reduces as you increase your air flow rate and is oxidized within the flame. So that's one more thing. And the third thing was, so that's what we have shown here. So your A and B, if you see, your A had a opening and where soot comes out, because you had completely fuel being coming there. And once you have fuel plus 20% of air, you see that the flame gets closed. And in this case, the 40% limit of formation of this 40% is the limit of formation of premixed flame. In this case, particularly in LPG plus air mixture, reactor mixture, if you are taking, this 40% is the limit of formation of premixed flame. Then and 50% and above, when you see, it burns as a rich premixed combustion. And it starts the flame height, and the flame height does not change significantly after this. After this, well, and one more important thing to remember is the radius of flame. The radius of flame is not changing much in all the cases that you see. The radius of this flame is not changing much. So that was the thing that you need to remember from the partial premixed conditions, then flame conditions, and then you were introduced into a topic called opposed flow diffusion flames. So in opposed flow, you have a oxidizer coming from some other part, and you have your fuel coming here, and you have your flame sitting over here at the stagnation region. So you will have a flat flame between both. So based on the momentum of fuel and air, so I'll write it here. So based on the momentum of fuel and air, the flame position is determined. So that's one important thing. And if flow are increased further, you see that the flame extinguishes due to an increased strain rate. So your flame stretches too much and eventually it extinguishes. So maybe I will write it down. So if flow are increased further, the flame extinguishes due to increased strain rate. So that was the case when you are having an opposed flow where your fuel and oxidizer are opposing each other, and then you are introduced into topic called diffusion flames from condensed fluids. So in condensed fluids, one of the important thing that you regularly see is your candle flame. So it is like solid or liquid fuel where your diffusion flames are formed. On their surfaces for such fuels. So for solid or fuel, liquid thing, on the diffusion flames are formed on their surfaces where your flame gets, where your vapors are being produced. So some simple examples are the candle flame. So you have a candle flame and you have your wick. So it creates a cavity here and this vapors comes out, and that's where you will have your flame being produced. Similarly, you can have it on a porous sphere through which your, say this is your porous sphere and fuel is coming through this. Eventually you will have a flame of this sort that you might have seen. And one more example for that interesting thing for this interesting application is the flame over the liquid pool. So you have your table, say, and you have your liquid being poured. You will see that your flame is having a shape of this particular form, which is also one form of your flames. This is one form of your flame or liquid pool condition. Then so then you were taught about learning what is instability in diffusion flames. So one of the major instability that you see is the primary instability involves the lift off or extinction that is present in candle flames. So say if you have a candle flame and say this is your primary and this is your thing, and as you increase your thing, you see that there is very less blue region that you see here and remaining things. So in this region it is completely black is what you see. You don't see any blue or orange flame being shown here. So the primary instability occurs is the lift off or extinction. So at increased fuel momentum, the residence time is not sufficient for the reaction to complete near the, or if I exit that area. So thus the flame lift off, and then in opposed flow flames, if the flow rates of fuel and oxidizer streams are increased, the strain rate of the flame process, and it extinguishes at a given strain rate, which is what we called extinction strain rate. So that's one more thing that you need to keep in mind. So I hope it is clear until now. Next, we will deal with next important topic that was dealt to you, taught to you was the turbulent pre-mixed and non-pre-mixed bits. So I hope this part is you remember. So next important thing that was taught to you was about turbulent, pre-mixed and non-pre-mixed ones. So in this, if you see, you have your table, and if you have a projection like this, you have your flow rate coming. This can interrupt and it can form eddies, and larger eddies can be formed. So the flow exhibits fluctuations which are random in nature. Such a flow with random fluctuations is categorized as a turbulent flow. So if you remember the things, there can be different parameters like velocity, temperature, species concentration, species mass fractions, and pressure, where these all variables now start showing random fluctuations in case of a turbulent flow, and the statistical averaging is used with variable defined as, say, you have a mean and a fluctuating quantity. So one important thing is the mean values are calculated for a time average over a sufficiently long time period. So you need to be waiting sufficiently long time such that then you calculate the mean values, so that the mean value does not change. Mean values will not change if you are increasing your time more. Then the time average for pressure, time in a sufficiently long time period, say long time interval, say you have T2 minus T1, that is nothing but delta T is nothing but your pressure, say for a given delta T. the mean value or the time average value. Can be written as 1 by T2 minus T1 integral T1 to T2, the pressure value at each instant. V of t is nothing but your instantaneous value of any property that you are interested in at any instant. So this basically it looks like, say you have your mean pressure, that is P bar, and over which you are having your fluctuations, which is nothing but P prime of t at a given point. So your P of t is nothing but P bar plus P prime of t. So your P prime of t is nothing but P of t minus P bar, which is similarly to velocity, temperature, species, mass fraction, anything you can be writing this into this form. Now then, in the intensity of turbulence, this indicates the magnitude of the fluctuating quantity. So from here, say intensity can be defined. So intensity is defined using RMS value, like that is P prime RMS is nothing but under root of P prime square over bar. So you square it, take a mean, and then take the square root of it. And we have the relative intensity as defined by RMS by mean value, which is nothing but your P prime RMS by P bar that you have. So these kind of random fluctuations are caused by several varieties in the flow, or so several variety or different ways of different sizes and different shapes of vortices that are formed. These are influence this flow, and a vortex is called as an eddy that you have. So if you write it in general, so your turbulent flow, it can have eddies of different sizes, and the molecular diffusion is enhanced by several times. When you are having a turbulent flow, the molecular diffusion enhances by several times. So the energy cascading happens. So energy cascading, where is nothing but where the main flow exchanges its energy to a large eddy, which exchanges it to a smaller eddy that you have, and this continues and so on. So it goes up to the maximum smallest eddy possible. Then finally it is dissipated by the smallest eddy, where your viscous forces starts getting dominated. Then, so there are 4 length scales that were discussed to So there are 4 length scales are defined to understand the features of a turbulent flow. So the first one is the characteristic dimension. Of the flow. Or the macro scale. So this simple example is your boundary layer thickness thing. So for jet flows, you can consider the width of jet as this value, whereas for pipe flows you can consider the dia of pipe as the characteristic dimension of the system. Now the second time scale is the integral scale, which is nothing but L0 is represented, or it is also referred to as turbulence macro scale. So this is nothing but the maximum possible length scale in turbulence. So this also represents this integral time scale, it represents the mean size of the medium to large eddies that you have in your system. I hope that is clear. Then the third time scale that is interested is the Taylor's micro scale. And lambda is represented, which is the intermediate scale which is weighted more towards small eddies, and it is represented as the RMS value of the velocity fluctuations, that is centimeter V RMS, by your mean strain rate. So that's what the value is, and if you remember, you might have seen this kind of form, that is your RMS velocity by under root of your change in gradient of the velocity square. This change in gradient of your velocity is nothing but your maximum, nothing but your strain rate. So I hope that is clear. Then you were introduced into the time scale called the Kolmogorov scale, micro scale. So this is the smallest length scale that is possible. This is the smallest length scale, and at this scale as mentioned, the viscous effects are predominant, and it is calculated as a function of kinematic viscosity, that is mu, and rate of dissipation turbulent kinetic energy and the rate of dissipation of turbulent kinetic energy. That is the epsa that you have. The epsa is represented. So here Coulomb length scale is approximately equal to your mu by epsa whole to the power 0.25, where your epsa naught is nothing but 3 times your r mass square by 2 by L naught by V prime r mass can be written. So I am not writing explicitly how you got and all, these were discussed in the lecture. So when you are having your Reynolds number for your integral scale, this can be written as almost V r mass L naught by your mu, and whereas for your Taylor's scale you have your V r mass into L lambda by mu that you have, and for Coulomb graph this you have V r mass square into L k by mu. So your integral and Coulomb graph length scale can be written as L naught by L k. This is approximately Reynolds number to F L naught, but 3 by 4 you get. Similarly for integral and Taylor microscale, here L naught by L lambda comes like Reynolds number L naught whole to the power half. So when you solve this, try to solve this turbulent things, you will come up with something called turbulent stresses, where so you know that actual turbulent flows are 3D in nature. They have time dependent in nature. So that is something, but they are chaotic fluctuations are present, and for solving numerically very small size grids and small time steps are used. In order to capture the Coulomb graph scale, you need to have a very small fine grid, and you need to have a very fine steps, time steps to capture that. So the turbulence modeling on the variables in conservation equation of say mass, momentum and energy, it can be written in terms of mean and fluctuating quantities, and they are time averaged. So then we get what is called the Reynolds averaged equations. So in this Reynolds averaged equations, there is an extra term at the end that you encounter. The extra term in these equations, which are called the turbulent or Reynolds stress terms. So you were shown some example of a 2D boundary layer. From momentum equation, where initial conditions like rho and u are constant. This was one of your assumption, and the other one is the gradient along the x is very less compared to the gradient in the y direction. And then if you write the equation, the partial equation, that is dou by dou t of rho u plus dou x of rho u plus dou by dou y of rho u v, which is nothing but dou by dou y of mu dou u by dou y. So this thing, if you are going to with taking the time average and writing variables as the sum of mean and fluctuating terms, and if you are neglecting the x derivative term for fluctuations, so we end up in equation of this form: dou by dou t of rho u bar plus dou by dou x of rho u bar plus dou by dou y of rho u v bar, which is nothing but, once you do, you will get mu dou u bar by dou y minus dou by dou y of rho u prime v prime bar. So this is the additional, that is the convective term, which is results in the Reynolds, also referred as Reynolds test. Here if you see the number of unknowns is more than the number of equations that you have once you are having the Reynolds distance. So this is leading to a closure problem. Now, how to solve this closure problem equation? So people use simplest models, which includes the eddy viscosity is one of them. So since you have dou by dou y of mu dou u bar by dou y minus dou by dou y of rho u prime v prime r, can be written as dou by dou y of mu dou u bar by dou y minus rho u prime v prime r, and this thing can be written as rho epsilon times dou u bar by dou y, which is nothing but minus u prime v prime r. So when you substitute all this, you are left out with dou by dou y of mu dou u bar by dou y plus rho epsilon times dou u bar by dou y is equal to dou by dou y of mu effective dou u bar by dou y. Here this particular term is the molecular viscosity that you have, and this term is the eddy viscosity, or what we call turbulent viscosity, and this is nothing but mu plus p epsilon that you have. So in short, turbulence increases the molecular diffusion, and if you see LES, like large eddy simulations, it reduces the large eddies and models the smaller ones. So that was part of your modeling thing, how people have tried it and all. Then in turbulent premixed flames, so that you see, so if you see a flame that has a contour like this, and you have different vortices around it. Now when you are having a simple laminar system, you have your cone like this, but when you are having a turbulent flame, this vorticity will be getting, so the eddies will be distorting your flame. So when flame becomes turbulent, the eddies of different sizes are involved. So when flame becomes turbulent, the eddies of different sizes are involved. This is due to interaction between the eddies and the flame zone. So the simple conical premixed flame becomes convoluted. So as we see here, so the different regions of turbulent premixed flames are based on the magnitude of reaction rate, then length scales, then turbulent intensity. So you see, we know that the laminar flame speed SL can be written as volumetric flow rate, that is UR by the area of flame. Now when you are having convoluted thing, your area increases, at the same time your volume flow rate also increases. So in short, your turbulent flame, so ST is way greater than your laminar thing. And there are different regions of turbulent premixed flame are understood by the laminar. So this is understood by the laminar flame thickness delta with different turbulent length scales. So there are three regions are available that you have. Is one is called the wrinkled laminar flame, where the delta is way less than your colmograph thing. So it's like your thin zone, but your particles cannot enter into this. So that's been the wrinkled thing. And then you have flamelets in eddies. So you have your smaller things out inside and bigger things there outside the zone. So this is condition where you have integral less greater than delta greater than colmograph. And then you have your distributed reactions where delta is way greater than L0. Now if you remember, an important non-dimensional number was introduced to you called the Damkola number, which states the characteristic flow time to characteristic chemical time. So this is estimate. Now you need to know the chemical time, which is estimated from laminar flame speed as delta by SL. So we can write it down into this particular form, and due to different length scale presence, that due to different length scales, the flow time may be estimated as can be written as L naught by V prime VRMS, which is nothing but your flow time, and the Ampere number is nothing but L naught by VRMS by L naught by delta into SC by V prime RMS. So when reaction rate is greater than your turbulent mixing rates, Ampere number is very greater than 1. So when Ampere number is very greater than 1, the reaction rate is worked or assumed in, that is assumed to be infinitely fast if turbulent mixing rates are much higher than the reaction rate, that is your Ampere number is very less than 1. Now if length scales are fixed, then the Ampere number decreases as the turbulent intensity is increased. Your turbulent intensity depends on turbulent Reynolds number that you have. So when L naught by delta times and V prime RMS by ST are less than, so the flame is, if it is laminar, when V prime RMS by V prime L is less than 1, or a wide range of length scales for us to accommodate is greater than 1, and so the wrinkled, therefore the wrinkling cases increase in overall surface area of flame, then your turbulence ST increases as ST by SL is approximately equal to function of V prime RMS by SL. So this is the form of one way of seeing into this. Turbulence and different plane speeds relation and all. So I hope, so we dealt in majorly with the turbulent premixed planes and the partially premixed and premixed planes. Then we saw some modeling things, how to model this stuff, and then we saw different length scales involved in a turbulent flow, and we learned some basics of what is turbulent flow and how you are, and some discussion on what is your basic introductions and what are the major things required for you during the study of turbulent flames and pre-mixed flames was discussed here. So we'll move on to the question and answer session. So here we have the first question in my hand. So the first question is, turbulence macro scale is a representation of smaller steady size, a ratio of RMS of velocity fluctuation to the mean strain rate, a function of turbulent kinetic energy, a representation of mean size of medium to large eddies. So I'll wait for 2-3 minutes for you to think of this, and then I will discuss the answer. The first question with us. So the question was turbulence. So the first question is about what is turbulence macro scale is. Is it a representation of the smaller steady size, the ratio of RMS of velocity fluctuation to the mean strain rate, or is it a function of turbulent kinetic energy, or a representation of your mean size of medium to large eddies? Which could be the answer for your turbulence macro scale, or in short it refers to your integral scale L0. So which could be your answer? You can provide your guesses. Maybe I'll wait for 1 or 2 minutes for you to just think about it and guess, and maybe you can give your answer to this question. Okay, so the correct answer for this question will be, so the integral scale. So turbulence macro scale is nothing but your L0, which is your integral scale. And this refers to is a representation of the mean size of medium to large eddies. So that's the answer to this question. So if you move on to the next question that I have. So the Reynolds stress terms are modified using large eddy simulations by resolving larger eddies and models the smaller eddies and models the larger ones. Individual components of Reynolds stress tensor, turbulent kinetic energy and form of eddy distribution. So I will wait for 2-3 minutes for you to think, and we will discuss the answer after that. question was the Reynolds stress terms are modeled using large eddy simulations by resolving. So the large eddy simulation, large eddies and models the smaller. So it large eddy simulations resolving the larger eddies and models the smaller eddies. So that's the thing that we use in large eddy simulations. So for smaller eddies we model it, and for larger eddies it is resolved. So that will be a correct answer. Now next, if you move on to the next question. In a turbulent jet, the velocity decay and jet spread rate is proportional to jet Reynolds number, or 1 by R Reynolds number, or Reynolds number to the power 2, or none of the above. So I will wait for 1 or 2 minutes for you guys to think about that. The question is, in a turbulent jet, the velocity decay and jet spread rate is proportional to. So jet spread rate, if you see, it is not related to your Reynolds number that you have, and the jet velocity is also decay is also independent of your Reynolds number that you are having. So it is not proportional to your Reynolds number. It is not 1 by eth of your Reynolds number, or whether 1 square. So it should be none of the. So in a turbulent jet, the velocity decay and jet spread rate, you can't directly is not directly proportional to your Reynolds number, or 1 by Reynolds. So that should be your answer. Now if you move on to the next question. When the ratio of laminar flame thickness to Kolmogorov scale is lesser than 1, then the burning region of our premixed turbulent combustion is well-chilled reactor, reaction sheet, wrinkled flamelet, corrugated flamelet. So I wait for 2-3 minutes for you guys to think of this answer, and then we will discuss. question lecture. Answer question. Yeah, current questions main answers.
Actually, TA subject మొత్తం కిందనే వేస్తాడు లేకుండా
Right. So the question was, when the ratio of laminar plate thickness, that is delta, to the colmograph scale is lesser than 1, then the burning region for cleaning stable and combustion is so when your ratio of your flame thickness to colmograph is less than 1, so that means your colmograph thing is either it should be very higher or your flame thickness is very low. So that condition is satisfied only when you are having a vehicle flame rate, where your delta is very less than Lk. So your delta by Lk will be very less than 1. That is like you have your flame thickness, but your things are much bigger, which cannot penetrate. So instead of flame being like this, it will be having a correlator. So I hope that is clear. Now if you move on to the fifth question. In a well-stirred reaction zone, Dam Coulomb number is equal to 1, greater than 1, less than 1, or none of the above. So I'll wait for 2-3 minutes for you guys to think of it. Yeah, so as we know, the Damkola number is nothing but the characteristic flow time scale to the chemical time scale. So when you are having a well-stirred reaction though, so your flow time scales will be lower compared to your chemical time scale. So your flow time scale will be less than 1. So that means your answer will be C. Next, in a turbulent jet flame, as the pore diameter is increased, its length decreases, increases, remains almost constant. None of them. So they are asking in case of a turbulent jet flame, as the pore diameter is increased, its length. I'll wait for 1 or 2 minutes while you guys think. So the question is, in a turbulent jet flame, as the pore diameter, so you add a pore diameter initially, and if you increase your pore diameter, its length of the flame will, so when you are increasing, you are having more flow rate, volume flow rate is increased larger. When your flow rate is increased larger, you should expect an increase in your flame height. So there will be an increase in the length of flame that you have. So I hope that is clear. Now we have a numerical with us. So consider a 0.6 meter diameter reactor, 9 meter long, operating at a pressure of 1 atmosphere. Reactants are entering at a temperature of 500 Kelvin into the reactor. Products are formed. They are reached at 1950 Kelvin and flow with a mean velocity of 130 meter per second. Now your relative turbulence intensity is 12% and your integral length scale is 1/10 of your characteristic dimension. Laminar length speed in centimeter per second can be estimated as a function of reactant temperature, as SL is equal to, an expression is given to you. Then the value of viscosity can be taken as 95 into 10 to the minus 6 meter per square second. Molecular weight of the products is 32 kg per kilomole. The turbulent Prandtl number can be taken as unity. If so, then the values of laminar flame speed, flame thickness, integral scale, turbulence intensity, turbulence Reynolds number, Kolmogorov scale and Damkola number is what they have asked you to find. So I will wait for 5 minutes so that you can try it out. Then I will. So we will first look into how to find the look into finding the laminar plane speed. So it is nothing but SL, and it is given as equation 0.000375 TU this power square minus 0.0995 TU plus 34.6. Here TU is nothing but 500 Kelvin is given to us. So if you substitute it here, substitute TU equal to 500 into this equation. If you solve it, you will get close to 78.6 centimeter per second as your answer. Now the second one, the flame thickness delta, which is something we can be written as 2 times alpha by SL. This is because as Prandtl number is equal to 1, your thermal diffusivity is equal to your momentum diffusivity. So therefore delta will be 2 times 95 into 10 to the power minus 6 by 0.786. So this comes close to 0.2417. Now the next thing that was asked to find was the integral scale. So in integral scale L0, if you see, it is given as 1/10 of your characteristic length. Now for a pipe, characteristic length is nothing but its dia, and dia is given as 0.6 meter. So if you substitute, there is nothing but 0.06 meter. And then, so you are given that the turbulence intensity, that is in meter per second, is Vrms, can be written as the relative turbulence intensity times your mean velocity of the flow. So your relative turbulence intensity is something but 12 by 100 times 130, which is nothing but 15.6 meter per second. Then your turbulence intensity is, so your turbulence Reynolds number can be written as Vrms into I0 by your mu. Vrms is something but 15.6 we got, into I0 is 0.06 by mu is 95 to 10 to the minus 6. So if you substitute here, you will get 9852.63 as your value. Then the next thing to find is the Kolmogorov scale. That is something like Lk, which can be written as V0 by Epsilon whole to the power 0.25, where your Epsilon is nothing but 3 times your Vrms square by 2 divided by your integral scale to the power Vrms. So if you substitute it here, you will get 3 into 15.6 square by 2 times 0.06 by 15.6. So this comes close to 94910.4. Now your Lk is nothing but 95 into 10 to the power minus 6 by 5180 whole to the power 0.25. So your collimatorial length scale comes close to 5.62 mm. And finally your gram collar number, which is nothing but I naught by Vrms by delta by SL. So here I naught is 0.06 by 15.6 divided by 0.2417 into 10 to the power minus 3 divided by 0.786. So if you solve it, you will get a value close to 12.51. So your option C will be your correct answer. So I hope this is clear how we have done it. So if we move on to the next question. The next question is ratio of turbulent flame speed to laminar flame speed is correlated as 3.5 Vrms by SL whole to the 0.7. For ethanol, laminar flame speed SL in centimeter second is correlated with the equivalence ratio given by the expression. So consider a mixture of ethanol vapor and air with 10% excess air flowing through a combustion chamber at a velocity of 7 meter per second. The relative turbulence intensity is measured as 8%. Then the turbulent flame speed for this case in centimeter per second will be. So that's the question. I'll wait for 1 or 2 minutes, see if you can try. Okay, since no one is here, so you can pause the video and you can look into the solution. So you need to find the turbulent flame speed. So you have your turbulent flame speed STL by laminar flame speed is given as 3.5 times Vrms by SL whole to the power 0.7 is given. Now your stoichiometric amount in kilomole of air required to burn 1 kilomole of ethanol is 3 kilomole. Therefore, the actual amount of air with 10% excess air is calculated as 3 plus 3 into 10 by 100, 3.3 kilomole per kilomole fuel. Now the equivalence ratio 5 is nothing but fuel by air actual to fuel by air stoichiometry, which is nothing but 1 by 3.3, that is for actual case, by 1 by 3 it is for stoichiometry. So you will get equivalence ratio 0.090 when you solve it. Now your laminar flame speed is nothing but 36.92, 0.140, 0.51 times equivalence ratio minus 1.1 square. So if you just substitute it, the value that you have got 0.909 minus 1.11 square, so you will get a value close to 31.25 centimeter per second. Now you got your laminar flame speed and So your RMS is nothing but relative your relative turbulence intensity times your mean flow velocity, which is nothing but 8/100 times 700, which comes close to 56 centimeter per second. Now therefore your turbulent flame speed is nothing but 3.5 times VRMS by SL whole to the power 0.7 into laminar flame speed. So that is 3.5 times 56 by 31.25 whole to the power 0.7 times 31.25. So this comes close to 164.53 centimeter per second. So this is your, so you got 164.53. So your option B is your correct answer. So this will be your turbulent flame speed that you have. So if I move on to the next question. So a turbulent butane jet of 1 atmosphere pressure and 300 Kelvin emerges out of a 25 mm port to the atmosphere. If the average temperature of flame is 1775 Kelvin and molecular weight of burned gases is 30 kg per kilomole, the value of flame height in meter is given, is what you need to find. So I'll wait for 1 or 2 minutes, see if we can try. So you can pause the video and check if you are able to do. So if you look at the answer, so from the with the semi-empirical relation, so your flame length turbulent by B is nothing but 6 times S plus 1 into rho E by rho F whole to the power 0.5. So now you need to find S, so that is found by using the stoichiometric air fuel ratio in mass basis for hydrogen for a hydrocarbon fuel. For a hydrocarbon fuel, CXHY is which is nothing but x can be written as x plus y by 4 times 4.76 times your molecular weight of air that you have divided by the molecular weight of fuel into 1. So if you substitute it, you will get 4 plus 10 by 4 times 4.76 times 28.84 divided by 58. So this comes close to 15.38 kilogram of air per kilogram of fuel. Now your fuel gas density rho is nothing but 101 P using the equation of state by 8314 times 300. So you get close to 2.356 kilogram per meter cube. And your mean flame density rho F can be written as 10325 into 30 by 8314 into 1775. So this comes close to 0.2059 kilogram per meter. So your flame length LTF turbulent is nothing but 6 times S plus 1 rho E by rho F whole to the power 0.5 into D. So you got 615.3 as your stoichiometric value, 38 plus 1 into 2.356 by 0.2059 whole to the power 0.5 into 0.025. So if you substitute here, you will get a value close to 8.312 meter. So your correct answer for this question will be option A, 8.312 meter. And yeah, so we have reached the end of today's session. So I hope, so in today's session we majorly focused on turbulent premixed flames and some part of your partially premixed flame thing. So in next session, on week 11, we will try to see much more on coal combustion and solid fuel combustion and all. And yeah, so thank you. So that will be a second last session for this course. So have a nice weekend. Thank you.